Joris Vankerschaver from Imperial College London to tell us about some surprises in geometric mechanics. So please.
Well, thank you, Cesare, for the introduction, and thank you guys all for coming. And I apologize ahead of time for my title. Nevertheless, I hope to be able to tell you some aspects of classical physics that you're very familiar with, but seen in a different light, the light of geometric mechanics. And this is going to be a little bit what the surprise part in my title refers to. And I hope these surprises will be genuine surprises and not the kind of surprises that we all remember from, when you're young and your parents are taking you to the dentist, and instead of telling you where you go, they say it's a surprise. So I hope it's not that kind of surprise. So roughly speaking, I'll be talking about three different problem areas in which I think that geometric mechanics has sort of uncovered some new useful insights, and these areas are related in the sense that they all have to do with mechanics, but they're not intimately related because of a problem or so. They're just areas where the same methodology works. And the first is going to be fluid structure interactions. And then the two others I'll be a little bit more vague about. So here I'll work out in detail what I mean. And then the others are going to be a little bit more high level. This is going to be about stochastic variational principles. And the last part, if there's time, will be about geometric numerical integration. So, for each of these problem areas, geometric techniques are quite useful. They give you some new insight and some things that, you could have done by other means, but maybe were a little bit hard to conceive of in an ad hoc way. So let me put this up here. So let me get started with the first part. So throughout I'm going to talk about, this is going to be a toy model that I'll analyze in detail, but I'll make various assumptions, but I'll also discuss a little bit what you can do to avoid those assumptions and to generalize. So the model that we're going to talk about, and this is very simple and for any physicist or for any self-respecting engineer, this is going to be laughably simple. So what we're going to consider is the motion of a single rigid body in an ideal or in an inviscid incompressible fluid. And in 2D. So these are all pretty big assumptions. So we have a single rigid body, fluid with no viscosity, which is incompressible, and two-dimensional on top of that. But as I'm going to argue, you can do this for multiple rigid bodies or for deformable bodies interacting with fluids. You can get rid of the incompressibility constraint fairly easily. This is no big deal. Three-dimensional fluids are not much worse. In fact, geometrically speaking, n-dimensional fluids work just as well. And this implicit assumption, this one is the hardest to get rid of. So adding dissipation is always a problem in geometric mechanics. But that's what the second part of my talk is going to be about. So if you're willing to go to the stochastic realm, you can dispense with this as well. So just to make a sketch, so we're looking at the rigid body from the top, and we have this body surrounded by fluid. And what we'll do is we'll write down its configuration by means of an angle specifying its orientation and a pair of numbers x and y specifying the coordinates of the center. So and we'll denote a triple consisting of the angle theta and x and y. We'll denote it as g. So if we have a rigid body like this, then g is specifies the configuration of it. And well, this is an angle, so it lives on the unit circle, and x and y live in R2. You can also think of that space as being the Lie group SE2, the special Euclidean group of rotations and translations, because in order to put the rigid body somewhere in the plane, you need to rotate it until its orientation matches what you want, and you need to translate it to bring its center into position. But we'll ignore this part. This is immaterial. So surrounding the body now, we have fluids, and I'll draw the fluid container bounded like this, although you can do everything in an unbounded container, just in order to draw this. And we'll denote the fluid container by F sub G. So this is the fluid container if the rigid body is at the location G. So the first really trivial thing to notice is that, well, obviously if the body moves, the fluid container is going to change, and that's why I make that explicit in the notation here. And so now how do we, so this gives you the configuration of the rigid body, and now how do we specify the configuration of the fluid? Well, the classical fluid dynamical way to do this is by specifying a labels to particles map which we'll write as curly phi, which tells you, well, if the fluid configuration is initially F identity or F0 or some container, and if the current fluid configuration is Fg, it tells you, well, fluid particle big X goes to position little x, and so on. So basically, if I can be just a little bit more explicit, so what I mean by this F0 is that at time t is equal to 0, when everything is in its reference configuration, you call that, well, you call this the reference configuration. And then at a subsequent time, the body might have moved to somewhere else. And this is Fg. We call this the current configuration. And then you can specify the fluid by giving a map from F0, from this exterior, to Fg, that exterior. And the map basically says, well, this fluid particle goes to that location, this other fluid particle goes here, and so on. So you specify the map, you specify the fluid by a map of this form. And this map, well, you want it typically to be 1 to 1 and on 2. You don't want particles to move into each other, and you don't want particles to split up. So, and you also, and this is maybe a little bit of an assumption, you want this to be smooth if you're modeling smoothly varying fluids, and to have a smooth inverse. So that makes phi into a diffeomorphism of F0 into Fg. So it's a smooth map from F0 to Fg with a smooth inverse. And not only is it a diffeomorphism, we're also thinking about incompressible fluids. So it's a map that preserves area, or in general preserves volume, and we'll denote those diffeomorphisms by S-diff, special diffeomorphisms. So that gives us all the possible fluid configurations when the rigid body is at that location. But now we still have to deal with the fact that, well, how do you take into account that the body moves, and that hence this space moves, this domain, and that hence this infinite dimensional diffeomorphism group also changes? Sorry? Yeah, it's not a group, it's a space. But it's, well, okay, since you're insisting, this is an example of a groupoid, or at least it's related to one. And in fact, this is maybe a good moment to do some historical background. So this introduction of diffeomorphisms into fluid dynamics is due to Vladimir Arnold in a seminal paper from the 1960s. And then there's been a flurry of work on this. So this is for fluids in the decades following this paper. And what I'm going to talk about here is based on 3 papers. One is by Deborah Lewis, Jerry Marsden, Richard Montgomery, and Tudor Ratiu, who's also here. And this is a paper from 1986 on liquid drop models. And then I wrote a paper also with Jerry Marsden and Eva Conso a few years ago. And recently there's been a lot of work on this by Henry, who's sitting there. So he's also a participant here, myself, and other people. So at the boundary, since the fluid is inviscid, we impose just slip boundary conditions. That's right. So you can have an arbitrary amount of circulation around the body. Like you don't make any assumptions. But this is just a configuration space. This is describing what's possible. Did you have a question?
So there was no slip or slip?
There is slip. So the fluid is viscid. It's allowed to slide around the boundary of the
And
region.
density is considered to be uniform?
Yes, density is considered to be unity, let's say. Again, you can bring it into the picture and have it be affected by the fluid flow. It's not such a big stretch to do so. Okay. So now, how do we tackle this problem of having the domain here be dependent on the rigid body configuration? Well, what we can do is So the fluid domain changes. And what we can do is, well, we can say, well, this thing changes as G changes, and there's no way to pick sort of a canonical representative of this space unless you have extra information or unless you're willing to break some kind of symmetry. So if all of these spaces are equivalent but not the same, then what can we do? Well, we can lump them all together in a big space and work with that instead. So we'll, and I'll make a little picture how this is going to happen. What we do is, so we want to collect all of these spaces into one space, and systematically the way we can represent this is as follows. Well, we have this geometrical object which is called a bundle. So what we'll do is we'll assemble all of the S-divs into a bundle. And systematically, so if this is my SE2, if this is the rigid body configuration space, what I have is, well, every point in this space determines the orientation and the location of the rigid body as listed there. And over this point, I have one copy of the fluid's configuration space, so F0, Fg. And if I change the rigid body configuration, over that point I have a different fiber, so a different fluid space, F0, Fg prime. And so for every point over that point or associated to that point, I have basically an infinite dimensional space telling me what the admissible fluid configurations are when the rigid body is at G or at G prime or wherever. And it turns out now if you take your G and you vary it smoothly, that these spaces, they change, but they also sort of vary in a smooth way. And maybe a little bit more to the point. What we can do is we can take all these vertical fibers and we can assemble them into one big manifold. And this manifold we'll call Q, and this is the fluid structure interaction space, or the fluid structure configuration space. So basically, the vertical directions, the directions of the fiber, tell you something about the fluid, and the horizontal directions, being, morally speaking, isomorphic to SE2, tell you something about the rigid body variables. And we also, so this is a three-dimensional space, this is an infinite dimensional space, and there's a projection going from Q down to SE2, and the projection basically maps points here back into SE2, and what it does, physically speaking, is points here tell you where the fluid is and where the rigid body is, and the projection throws away the fluid part and just keeps the rigid body part. So to be precise, so pi goes from Q to SE2, and it takes a fluid structure pair and throws away the fluid. So okay, up to this point everything is pretty formal and pretty standard, so maybe I'll speed up a little bit, but now we're getting to the interesting stuff. Now let's change tack a little bit and ask ourselves a very simple question. And the question is, well, what happens if you move the rigid body. And let me remind you, so the fluid is considered to be inviscid. The body, we'll say, is just elliptical shaped, so it doesn't have any sharp edges or anything. So under those two assumptions, if you take the rigid body and if you move it around a little bit, the fluid is going to experience some velocity. And the fluid, before you move the rigid body around, the fluid might have had some vorticity. And when you move the rigid body around, the vorticity will be advected and spread out. But by moving the rigid body, since fluid is inviscid, you cannot take away vorticity or you cannot create any vorticity. That's just simple fluid dynamics. So we have the constatation that we cannot create or take away vorticity.
Sorry. Do you require continuity of the normal component of the velocity?
Yes.
The body?
Yes. So I'll get to that in a point, but we want the normal component of the fluid velocity to match up with the normal component of the rigid body. So actually, let me get to this right away. So systematically, what we can do is we can say, well, given a rigid body velocity, we can associate to that the corresponding fluid velocity. So I'll call that U sub body. So this is the fluid velocity generated by moving the rigid body. And this U sub body is going to be a gradient vector field because you cannot create any vorticity nor can you take it away. And since the fluid itself is since fluid is incompressible, U is divergence free, so phi has to be a harmonic function, and as you say, the normal component of the rigid body velocity must equal the normal component of the fluid velocity. So we have boundary conditions that say that the normal derivative of phi must be equal to the normal derivative, the normal component of the rigid body velocity. So the point here is that, well, you just have a system that's very well known from classical fluid dynamics. To solve this, well, you have to find this harmonic function with these Neumann boundary conditions. You can do that, and the boundary data sort of depend or are given in terms of the velocity of the rigid body. So we can see we effectively have a map that takes rigid body velocities into the corresponding fluid velocities. And this map I'll call H. And in fact, H, if you chase through all the definitions, H is a horizontal, an example of a horizontal lift operator. And systematically, what this does is, and the reason why it's called a horizontal lift operator is basically H takes a tangent vector to this space, so a rigid body velocity, and it translates it into a tangent vector in this space, So this space here has the degrees of freedom for the rigid body and for the fluid. So this tangent vector here is going to be omega comma v, and then h of omega and v. So sort of goes in the opposite direction of the projection. It tells you, given the velocity of the rigid body, here's the velocity, the corresponding velocity of the fluid. So why is this interesting, and why do we even care about this? It's because, well, these horizontal lift operators, they're on the same footing as connections or covariant derivatives in geometry. So if you have a horizontal lift operator, you can turn it into a covariant derivative, and vice versa, through some technicalities. And now, why is that a good thing to have? Well, now we can sort of use our Riemannian geometry toolbox and figure something out about fluid dynamics in this way. And in order to do this, I'll sketch a useful analogy. So if we want to tell our students about Riemannian geometry, and about curvature and parallel transport and all of that stuff, what we usually do is take a curved surface, let's say a sphere, and one way to explain to explain the curvature of the sphere, for instance, is to say, well, if you're a soldier or a Roman centurion standing at the equator in this point, and you have your sword pointed in front of you, and you march towards the North Pole, all the while keeping your sword sort of pointed ahead. And then once you're at the North Pole, you don't change the angle of your sword, but you just go back to the equator by taking steps sideways. And then once you're at the equator, you go back to where you came from, taking your sword or your tangent vector along with you. Then once you end up back where you started, you'll see that your tangent vector or your sword, or however you want to call it, will have undergone some rotation. In this case, rotation of pi over 2. And we say to our students, well, the fact that you take this vector and you parallel transport it along this loop, the fact that you don't come back to the same vector means that the sphere has curvature. And more specifically, what we say is we have a holonomy. Namely, we have to do a rotation, or we have a rotation over pi over 2. And this is a rotation in 2D. And this is a consequence of the fact that the sphere is a curved manifold. Now, so here we have this kind of effect arising from the fact that the sphere is curved. So now for fluid structure interactions, there's a similar effect. And basically it has to do with that map H that I sketched over there. So H allows us to take the rigid body and move it in any direction that we want. So now what we'll do is we'll take our rigid body and we'll move it through the fluid in a closed loop. Any closed loop will do, big or small. smooth or not, like as long as it's piecewise smooth. So what happens when we do that is we entrain the fluid as we go along, and then once we get back to where we started with our rigid body, what will happen is that the fluid in general is not going to come back to its original location. So in general, there's going to be some drift in the fluid particles that we can compute or that we can measure, and so on. So this drift, how do we capture it? Well, if the rigid body starts at and comes back to location G, the drift in the fluid is given by a map phi, which goes from Fg back to itself. And in fact, it's not any old map, it's a special diffeomorphism of Fg. So that doesn't really matter, but what we have here is that the drift in the fluid, after doing this cyclic motion with the rigid body, arises in precisely the same way that this Riemannian holonomy arises on the sphere. So what we have here is basically S diff valued holonomy. So basically, every time you take a cup of coffee and you stick a spoon and you stir around, every time you why not?
Because the reason why there is motion in the coffee is that there is adherence to the bound.
That's right, but if you're sort of taking dry coffee, or if you, well, let me say, see.
So there is a force. There is a force that you're and that force is absolute here.
But here there's also a force. Like it's just you're in the invested regime, so there's also a force.
Okay, never mind. This is about parameterization, not about.
Right, but do you agree that it's at least?
I mean, so far I didn't say anything, so I agree.
Oh, okay. Well, be that as it may, okay, maybe coffee is a different is a difficult example, but sort of if you're willing to abstract away, you can sort of see that this structure is in there somewhere. So now, let me continue here. So now we have a problem and a solution. The problem is that in general, this phi, you cannot compute it analytically. You have to compute it numerically or guess it in some way. But the good thing is, if the size of your loop is very small, then there's an approximation that we can compute. And so I'll label this as a possible solution. For small loops, phi is roughly proportional to a tensor that I'll call B for just a second. And let me make another drawing. If the position of the body is here, and if we execute a loop along a small loop whose sides are parallel to vectors x and y, then there's this tensor B, so that if we evaluate it on x and y, as long as the loop is sufficiently small, we get something out that is a good approximation to our holonomy. And this B tensor is given in terms of another tensor by means of a very simple formula. And here this A, to put the dots on the I, it's related to the H map, to the horizontal lift, but to be more precise, it's the connection one form associated to H. So two things I want to say about that. This is just geometric nonsense. The only thing that matters is that A is given in terms of H and vice versa. The thing that's important is this formula right here is something that you might remember from gauge theory. This is Cortan's structure formula to compute the curvature B. This is actually the curvature in terms of the connection one form A. And it's an algorithmic thing, you can compute it. And just to hammer on this a little bit more, just in case you think that this A is a very abstract and not relevant concept hidden in the geometry somewhere, what this A does is it actually has a very nice interpretation. It takes a rigid body velocity and an arbitrary fluid velocity, and it takes the projection onto the divergence-free part in the Hodge decomposition. So this is the projection onto divergence-free part in the Helmholtz-Hodge decomposition. So it's actually a fairly natural map to consider. Now,
Why does it forget V?
Sorry?
Why does it forget V add-on?
It doesn't actually forget V because if you do the Hodge decomposition, you
Okay, so what's U?
so you
That's the boundary conditions that you put there.
sorry.
That's
Oh well,
you have only the gradient of phi, right?
that's right.
Okay, thank you.
So basically, what A does in another way is it subtracts the gradient of phi from U. Little u there has its normal component lining up with the normal component of the rigid body velocities, and then the Helmholtz-Hodge decomposition is just decompose u into something that's tangent to the boundary and into a gradient part, which is precisely this, and it's that you subtract when you do that projection. So to wrap up a little bit, so there's one extra thing that I wanted to say about. Now, what about finite loop? So let's say you want to control fluid particle by doing some finitely sized loops, not just infinitesimal wiggles with your rigid body. Then what happens is and okay, let me maybe be a little bit vague here. You can relate phi now not just to the curvature B, but you can specify the holonomy that you get from a finite loop in terms of B and the covariant derivatives of B. So this is basically this is a set of vector fields, and it generates a vector space of possible directions that you can access in the fluids by doing small loops or well, finite loops with your rigid body. And where does this come from? Well, this is a theorem from geometry that basically tells you how to assemble these invariants and how to compute them and how to get the resulting holonomy out of it. Now, what does that buy you in terms of understanding the fluid? Well, all of these guys are divergence-free vector fields. So, in particular, they have stream functions. And by looking at the stream functions of each of these guys in this series in turn, you can sort of estimate what the fluid is going to do up to a certain order. So one thing that we did is we looked at just, this is a very stupid toy model, but well, our paper sort of analyzed this a little bit more in detail. And we actually got some kind of prize for it, so it's probably not all wrong. But you have a fluid particle and you want to control it, attract it, or repel it, or steer it by means of, you can move this rigid body about. And what happens is the stream functions of this contribution to the holonomy look like concentric circles. So this is to first order. And then the stream functions of the second order, the covariant derivative, well, there are two covariant derivatives, one in the x and one in the y direction. They look like hyperbolic vector fields like this. So this is second order. And you can go on, so computing its curvature and its covariant derivatives. These are all rational functions, and you can compute these things with a computer algebra package. But you can sort of get an idea for what the particle is going to do. So it's broadly going to go around the rigid body on closed loops like this. And if you want to attract it by moving the rigid body about, you better find a control strategy that activates these modes so that, well, the particle gets attracted like this or like that. And now to be incredibly vague and general, it turns out that in the limited sort of framework that I've sketched, knowing this guy basically tells you everything you need to know about fluid structure interaction. So if you write down, say, so if you do this kind of control, where you control a fluid particle by moving a rigid body, everything is traced in terms of B. If you look at point vortices interacting with the rigid body, or vortex rings in 3D interacting with the rigid body, the interaction terms will turn out to be some combination of B, or some invariant of B. So in general, as long as you can compute this, you can understand fluid structure interactions in this framework at least, in sort of a very geometric way. So I'll finish fluid structure interactions here, and I'll just say, because I'm going a little bit over time, I'll just say 2 words about the other topics. So actually, I'll just need half a blackboard for that. So it turns out, as I said, and I actually probably just erased it, you can get rid of all the assumptions about the dimensionality, compressibility versus incompressibility in a fairly geometric way. The only problem is, well, what about viscous flows? And the answer is, well, there's a very nice, also geometrical, in a sense, framework for that. And there's a number of groups that have made contributions to that. And so there's the work of Peter Constantin, who's here with us, and his former student Gautam Iyer from, I believe, 2005. And then there's a group in Portugal around Cruzeiro, Arnaudon, and Cipriano. And I want to say it's also from more or less the same era. And the main idea, and this is the only thing that I'll sketch, and then I'll let you go. So the main idea sort of is, well, for the Euler equations, and here we're just talking about fluids in a fixed container. There's no moving boundaries whatsoever. But as I've hinted already, the trajectories of the Euler equations, or the solutions of the Euler equations, describe curves on the group of special diffeomorphisms. And here it's just of one fluid container. Fluid container doesn't change. So you have one curve tracing out a path in this group. Now for so here we have curves on S diff. For the Navier-Stokes equations, actually what you can do is you can replace curves, so deterministic curves, by stochastic processes on the diffeomorphism group. So instead, so now for the Navier-Stokes equations, you, in order to be a bit more technical, you have S diff valued semi-martingales. And basically, on a very low level plane, why is it a good idea to look at stochastic flows like that, or stochastic processes? Well, if you think about Ito's formula for the chain rule, you have the Ito correction term, which involves sort of second-order derivatives, Laplacian in some sense, and well, the Navier-Stokes equation, well, what distinguishes it from the Euler equation is, well, apart from the boundary conditions, well, there's a Laplacian in there. So I'll leave that at this, just to say that, well, there's some things that you can do even to tackle viscous flows. So for the last part, if I could have the screen lowered, please. Screen. Actually, I can probably sketch it real quick on the blackboard, then we don't have to, wonderful. So this is going to make it a little bit more pleasant. So for the last part, I wanted to say something about, if you have all these continuous equations, how do you discretize them and turn them into difference equations? And it turns out that if you look at the geometry, you can also do this in a, I guess it's coming. You can also discretize these equations in a way that respects the geometry and gives you like long-term very good behavior. And the trick basically is, so normally what you would do is, if you have differential equations, you discretize them, say, by finite differences, and you get some kind of difference equations. But it turns out it's a much better idea, at least if you have a mechanical system, to do the discretization on the level of the Lagrangian or the Hamiltonian. So for instance, what I've sketched here is if you have a Lagrangian which depends on time, which depends on positions and velocities, if you do the discretization in the Lagrangian and you replace the velocities by finite differences, say, this is but one choice. You can also get a version of discrete Euler-Lagrange equations, and the flow of these discrete equations has a number of very good properties. And here's an example. If you take just kinetic minus potential energy, and you replace the velocities by finite differences, and the positions by centered approximations, then the discrete Euler-Lagrange equations that you get from that are the implicit midpoint method. So you don't necessarily get new stuff. You just get, well, sometimes you get new things, and sometimes you see that the old stuff is actually pretty good as well. And what are the advantages? Well, first of all, it becomes really easy to compute the order of the ensuing methods, because the order that you chose to approximate the Lagrangian will determine the order of the methods. The methods are going to be guaranteed to be symplectic, or their flow is going to consist of canonical transformations. And it also becomes easier to analyze conserved quantities. This backward error analysis I'm not going to talk about, but this is just a meta theorem that says if you have a symplectic integrator, then there's a lot of good properties that sort of are magically given to you because of symplecticity. And one of the practical outcomes is that variational integrators have excellent long-term behavior. And I've just taken one typical system where you have point vortices on the sphere, and here, like we've come up with a variational method which sort of has this bounded energy error, whereas Runge-Kutta of the fourth order just its energy increases linearly. So our method is only a second order method, but it still energy-wise does a little better, at least in this metric, than standard method. And why is this good? Well, if you want to do statistics of point vortices, or if you want to run long-term simulations, like for instance, if you're looking at simulations of the solar system, then you don't want energy to be artificially pumped into the system. Otherwise, you would have all sorts of disastrous things. So this is a way to, in a very simple way, to come up with numerical integrators that have very good long-term properties. So I'll stop here, and sorry for going a little bit over time. Thank you very much.
Okay, thank you very much. Questions?
So this, with the Tia-Singer theorem that you use, so phi is going to look something like a Taylor series?
That's right, yeah. There's, it's actually called the Magnus expansion, so it's not exactly a Taylor series. Well, it has a bunch of other stuff, because when you do your series expansion, you're manipulating things that are not commutative. So when you do all the work, you pick up terms that look like, that sort of give rise to, if I can lift this, these higher order derivatives. So yeah, that's more or less it. So it's like a non-commutative Taylor series in a sense.
Any more questions? Actually, I was thinking about something. When you mentioned this way of inserting noise into this Lagrangian motion on the spatial diffeomorphisms. So there is this Lagrangian Euler-Poincaré type formulation of collisionless Boltzmann type equations in kinetic theory. In that case, you replace diffeomorphisms on the configuration space with diffeomorphisms on the phase space. Okay, so does it even make sense to implement this idea and see whether you can get something like Fokker-Planck type equations on phase space?
I think so, yeah. We've tried various things Earl and I, but
So these things just work.
well, to be honest, we don't really have a good intuition of why it works
But
and
it
what
does.
you can do with it. Like for instance, one of the things that I couldn't do was find like a matrix group analog of this. So I'm a little hesitant to say it will or will not work. We should talk about it
Yeah.
during the rest of the program.
Okay. So thank you very much.